before the collision of number 2. And so if I move this to the other side, this says a negative 0.5 kilograms times speed 2 must equal to 6 kilogram meters per second is what I get here. And so to finish this calculation, I would move this over to here, or divide. Kilograms would go away. And 6 divided by a half is 12 meters per second, and then with the negative is negative 12. So to recap this, a speed of negative 12 at a half a kilogram is a negative 6. When I add that to the one going in the positive direction, number 1, that has a momentum of a positive 6, I get a total of 0. So these have to have a total momentum of 0 before the collision, because I'm trying to get them to stop, and I know stop means 0 momentum after the collision. And so these problems can now start to get a little tricky. But know this: you ever see a problem that says collisions, says interactions, 2 objects, jump to momentum and know that the momentum before is equal to momentum after. It doesn't matter what they are. They could be carts, they could be trains, they could be boats, they could be insects. I was about to say your book, but I'm thinking of the 101 book, has a good problem about a big fish who gulps down a little fish. And the little fish is swimming this way, big fish goes down, he gulps it down, and that's a collision. That's an interaction. So sometimes you won't see the word collision, but you got to visualize what's going on. 2 trains, a train and a car, a nitrogen molecule and an oxygen molecule, but as they bump and they rub into each other, that's a collision. And know that it's conservation of momentum. Well, I'll do one more, and then I'll say, hey, that this will be a good place to stop our first 6 chapters. But I would say, again, and like I said, I don't know how many I should do to really get this to sink in, but I'll just keep saying it's a very, very powerful tool. And it's fairly easy to use once you recognize it. All you need to say is I have an interaction, I have a collision, I have 2 things interacting, and so what I do know is the momentum before is equal to the momentum after. Does it matter that they're big objects? No. Does it matter if it's the Earth? No. Does it matter if the objects are red? No. Does it matter if they're going fast? No. None of that matters. And that's why it's really, really, really powerful. The one I like to show here is, what if I actually then start them hooked together at rest and then release the plunger? I think you just saw that by releasing the plunger, this one went kind of fast and this one went kind of slow. Now, I could have released the plunger like this, where they actually have the same mass. And if I do that, looks like they go at the same speed. But to finish up the chapter and not get bogged down on all the possibilities I can do, but hopefully what you're getting is that you could now do all the possibilities, and so the one that you see on the test may not be exactly these 4, but you will see an interaction, you will see that it's conservation of momentum. And so what do I know about this when I release this? What would the conservation of momentum tell me? And as we'll see here, there's some information, maybe not all the information, like I can't get exactly what this speed is, but I will see that one has to be positive and one has to be negative. I will see that this one has to be more absolute value positive than this one is, speed is negative. Or we will even go further than that. We will see that this speed has to be 3 times that speed. And maybe some of you are already seeing it in the math, but let's set it up. Again, I would make a little chart here and I would say, okay, here is before and here is after. And so before the collision, it looks like this. And I would have the mass of number 1 with a speed of 0. And the mass of number 2 with a speed of 0. And so I would have 0 momentum before the collision. Hopefully that was obvious without actually plugging the numbers in. Then when I release it, I would have the mass of number 1 and its speed, and then the mass of number 2 and its speed. And of course, notice these would not be the same speed like they were in the last couple of ones where they were hooked together. Now I guess the first one, they were not hooked together, so they were different, although I knew what this one was. It was a 0. And so this one, I do not know what the individual ones are. That's why I would say I can't solve this completely, because what I do have is one equation but 2 unknowns. And so I think you're kind of familiar with your algebra, where if you have 2 unknowns, you have to have 2 equations. So I'm not going to be able to solve this harder one completely, but I can get some very useful information. Again, watch this. If I then say, okay, let me take this to the other side, so negative 0.5 kilograms times V2 has to then equal 1.5 kilograms times V1. And if I cancel the kilograms, and maybe I'll even take that negative 1/2 and put it over here, so this becomes negative 3. I see those 3 pieces of information that I said would fall out. And the first one is, I will see, in terms of magnitude, the speed of number 2 is bigger than the speed of number 1. And so sure enough, I release it. Yep, that speed is bigger than that one. And the other thing I said is it'll be 3 times bigger. Yep, sure enough, that's what this math says. It's 3 times bigger. And the third thing we see in this math is that the direction of them are opposite. And that's what the negative is saying. So the speed of number 2 is the negative of number 1. And so this second one goes in the positive direction, but the first one here goes in the negative direction. And sadly, I can't actually have a number for either one of those. Of course, obviously, if I have one, then I have the other. So if I had more information, I may be able then to get the speed of 1 or number 2. But once I get 1 or number 2, I can get the other one. But for what we've done so far, I would have to stop. Now, as we get to chapter 7, we will add to that, and we will be able to figure out number 1, and which will then mean we need number 2, and that's that principle of conservation of energy I was talking about. So we'll build on this, but that's coming up. And so I'll call it quits and say, okay, we are now done. We are done with chapters 1 through 6, and as promised, we've still got quite a bit of time on our clock here. Actually, I wanted to save an hour. I didn't quite save a whole hour, but since we're not face-to-face, I might still just talk a whole hour. So if I go a little long, this is really for your benefit. If you don't want to, watch the test review, you don't have to. I will point out that I'm not saying anything new, but I am trying to give you a summary, and I am trying to give you a heads up. This is the kind of thing that would be in a face-to-face setting. I would say, now would be a good time for questions. And those of you who don't want to hang around, you can go. But those of you who just want to hang around for another hour, I know class is done. You can ask me a lot of questions. Let's talk about the test. So that's normally what I would do in a face-to-face, and we don't have that here in our weird pandemic world that we live in right now. So in place of that, I just wanted to keep talking, and so you can just keep listening for as long as you wish. I will start this little 6-chapter review by clearing the board and starting to mention kind of the structure of the test. Excuse me, getting a little hoarse. But the structure of the test is this, so you're not surprised. When you open the exam, or it unlocks at 11 o'clock on Monday, the first half of the exam will be multiple choice. And the second half will be what I call free response. That is where you'll actually do a calculation. Now, remember, there are 6 chapters here. And so in the multiple choice, I will make 2 multiple choice questions per chapter. Okay? And so the structure of test number 1 will look this way. There will be, and I'll just put 2 multiple choice questions per chapter. So that means we've got 6 chapters. So 6, I'm sorry, I said that wrong. I meant to say 4. Sorry, the free response is going to be 2 per chapter. So, forgive me. Let me start again here. There's 4 multiple choice per chapter. There's 6 chapters, so you're going to have 24 multiple choice questions. That's what you'll see at first. I haven't written them all out, so I'm not sure how many pages it will be. But what you want to do is just print that out and then read it and then circle A, B, C, or D and go through all 24. And that's going to be the first, it'll probably be about 3 pages long. So that'll be the first 3 pages that you're going to scan and you're going to turn in. Okay? Then the free response. Question will be 10 questions. And I'm going to go ahead and say that that is 2 per chapter, but that's not counting chapter 1. Remember, chapter 1 was just converting units, I think scientific notation. So there won't be any of that. And so it will, actually let me rephrase that. It's not that there won't be any of that. Converting units will be inside the multiple choice questions and the free response questions. So you may be given something in centimeters, but you need it in meters. And I'm going to demonstrate that. But there won't be a direct question like that. So what I mean by that is the 2 questions, we'll start off with 2 questions from chapter 2, then 2 from chapter 3, then 2 from chapter 4, then 2 from chapter 5, and then 2 from chapter 6. And so there'll be a total of 10 questions based upon the free response. All right, so I made a little list here of what is in each chapter. And chapter 1 had things like converting units. That was a big thing we focused on. And so I will then take a moment here to say, this is the kind of thing you're going to be looking for, okay? As I said, they probably won't be, and they definitely won't be in the free response questions. They'll be more in the multiple choice. For example, earlier in today's lecture, in lecture 1, I said that the distance from the Earth to the Moon is 240,000 miles. Okay. This might be a little tough one, but how many meters is that? Now remember, this is open book. And so you'll look into your book and you will see that it says there is 1,609 meters in 1 mile. And so what I was trying to show you in chapter 1 is you could easily convert by treating your units and your prefixes with the same rules of mathematics that you do your numbers. And so if I had, said something like this, 5x equals, and question mark, but I also told you x equals to 3. Of course, what you would do is put in the value of 3 for x. You call that substituting. And then you would finish it up and get an answer of 15. And so I'm really kind of saying the same thing. In place of miles, see a mile, I would put 1,609 meters. Another way of really saying the same thing, and maybe I'll put it over here, is to start with the 240,000 miles and then say, I won't change anything. I'll just multiply it by 1. But this fancy 1 is really the same number over itself. Because remember, 5 over 5 is 1. And so that means 1,609 meters over 1 mile is 1, right? 1,609 meters is the same as 1 mile. And then, of course, miles cancel off, and you're back with the same thing. So whichever way might be a better way for you to think about it, you're going to get this same answer. And so I will take the 240,000 miles and then multiply by 1,609 meters and come up with 386160000. I think that's it. 4 zeros, 16, yeah. And then that would be meters. And one other thing that we roughly touched on was writing things in scientific notation. So maybe I'll write this as 3.8616. And then count 1, 2, 3, 4, 5, 6, 7, 8 meters. And so that's maybe the question, what is the distance to the moon in meters written in scientific notation? So those are kind of the simple things. Maybe I'll just do another one here. Maybe I would ask, how much time does it take in seconds for the Earth to go around the sun? Now, I guess I'm assuming by that you know what a year is. If you don't, let me explain. A year is defined as the time it takes for the Earth to go one time around the sun. So, in that question, I have indirectly said 1 year. Right? I'm asking you, how much time does it take in seconds for the Earth to go around the sun? That's 1 year. And so notice that if it just asked how much time, you could just write 1 year and be done. But it says how much time in seconds. So I need to convert this. And so I'm going to take 1 year and kind of do the same little thing I did. And maybe I'll do it this way here. If I multiply it by 1, I don't change anything. But if I call this a clever one, that is 365 days is the same as 1 year, then year would cancel with year and you'd be left with days. And so if you just multiplied that out, you would have 1 times 365. And so you would say, okay, it's 365 days. That's how long it takes to go around. So if it asked how many years did it take to go around, the answer is 1. If it asked how many days, it's 365 and a quarter, if you let me throw in a little bit. But let's just call it 365. Let's not worry about the odd number in the leap year. But it asks for seconds. So I think the next thing I would do is to say multiply by 24 hours. which is the same as 1 day. So again, notice I'm not changing anything because I'm multiplying by 1, but what I am doing is changing the units, and so a day would cancel with day, and so I would now have 24 times 365 times 1, and that would tell me the time it takes in hours to go around. And if we continued here, we could say then there are 60 minutes in 1 hour. An hour would cancel with hour. And so now I would have how many minutes. And then finally I can get to my answer, which is then how many seconds. And so notice, I started with a year, and I multiplied by 1. I multiplied by 1. I multiplied by 1. And I multiplied by 1. I didn't change anything. I still have 1 year. What I did change, though, is the units. And so I will have so many seconds left here. And I'm pretty sure, I'll get my calculator, but this is such a common number, and you see it so often, or at least I see it so often, that I think it's 3.15 times 10 to the 7th. Let's see, 1 times 365 times 24 times 60, I'll just go 60 squared. Yeah, 3.15, and then 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. And so there's the number in seconds. All right, so hopefully that's maybe the easiest of the stuff I can review. That's kind of the thing you want to be looking for here in Chapter 1, is just converting of units. And so it may be a direct question in the multiple choice about converting units, and there'll be maybe 1 or 2 like that. Because remember, there's going to be 4 questions, 4 multiple choice questions from number 1. But when it comes to the calculational stuff, the free response, maybe you'll convert units within a problem. You know, maybe it'll be a problem on, say, Newton's universal law of gravity, like I did in the lecture. I gave the distance in centimeters, but you have to input it into that formula in meters. So you got to do your converting there. So that's what I mean by there wouldn't be a direct free response question from Chapter 1, but it'll be there somewhere in the other pieces of it. Okay, so then I was looking at, okay, what did we do in Chapter 2? And Chapter 2 was a chapter which we called Describing Motion. And it said what is speed, what is velocity, what is acceleration, and what is the difference between all of those and those calculations. So hopefully what you got out of Chapter 2 then was that the distance something traveled is equal to, and let me put a bar over it, it's average speed multiplied by time, and the acceleration is the change in speed over time. And again, let me be really, really, really careful here, because speed and velocity are not the same thing. In fact, they're so close, or I should even say they're close, but I think they're just confused by students. But I'll say it again, if you have this airplane flying along at 600 miles an hour, and it keeps flying with 600 miles an hour, I mean, it's going really, really fast. So what's its acceleration? 0. Because acceleration is not a measurement of its speed. Acceleration is a measurement of how its speed is changing. So it could have a big speed or a small speed. That really doesn't matter for the acceleration. The acceleration is a separate measurement, separate from speed. Big speed does not mean big acceleration. Or the other way around, big acceleration doesn't mean big speed. Oh, let me try this one. I take this marker, I throw it up. Okay, on the way up, what's the acceleration? I hope you're saying 9.8 or roughly 10 downward. Okay. Then it gets right to the top. What is its acceleration? Don't say 0. Its speed is 0 at the top. And so it has a very small speed. 0, yes, but it's changing. It's going from up to down. And the acceleration, even at the top, is still 10. And so the acceleration of free fall is 10. The object is going up or down or at the top. It doesn't matter. The acceleration is always 10. And go back where we filled some of those charts. You'll see at the highest point, we did this one where we tossed the ball up, and at the highest point, we were 3 seconds into it because we had thrown it up at 30 meters per second. And at that top, the speed was 0, but the acceleration was 10. And so that's kind of my little warning here, is they're talked about in the same chapter, but they really are different things. And so hopefully don't confuse them. Maybe some examples of a calculation would be something, a free response type of question would be something like this. Let's say that I stand on the edge of a very tall building and I ignore air resistance. Oh, I bumped my microphone again. See if I bumped it out. No, looks good. All right, I think we're still good. So I'm standing on the top of a very tall building, and I let the ball go. And if I can ignore air friction, it's going to go faster and faster and faster. And I might ask this question. And listen carefully to the question. The question could be one of two ways. It could be, say, something like, after 10 seconds, how fast is it going? Don't confuse that with, after 10 seconds, how far has it gone? Distance, speed, acceleration, all connected together, but don't confuse them. So let me start with that first question. How fast is it going after 10 seconds? I guess I would do this. I would say the acceleration then is 10 meters per second squared. The time is 10 seconds. So the change in velocity would be 100 meters per second. Now, I suppose I'm not technically done because final speed minus initial speed is what I just calculated. I did not calculate final speed. However, I did say I released it. And that was a subtle way of saying the initial speed is 0. So how fast is it going after 10 seconds? About 100 meters per second. And I'll give you the option. You can, use the 10 or the 9.8 during the test. If you use the 10 like I just did, you probably don't need a calculator. That's what's kind of nice about it. But if you want to do it a little more accurate, then get out a calculator. And so this would come to be 98 meters per second. That one you don't even need a calculator for. But most of the time when you do 9.8, you're going to need your calculator. And that's fine. You use a calculator or don't use it. I'm after your logic. And in this free response, I'll go through your logic. And I will grade it on 3 points. And I'll kind of go through here and say, oh yeah, they almost got it. So they get 2 out of 3. They were really close. They kind of messed up with just a small little detail. Or, of course, maybe it's a 2-part problem, so they did half of it. So, okay, so there's 1.5 points, and they lose 1.5 points. Or maybe they kind of got the right formula at the start, but everything's just totally wrong. And so it's like, okay, that's 1 out of 3. Or maybe you didn't do anything, so there's 0 out of 3. And so that's kind of what I'll be grading for, and it'll be broken down into those parts. Do it all right, you get a 3. You don't do anything, you get a 0. 2-part problem, you do half of it, you get 1.5. You do it mostly right with a little bit of wrong, you get 2 out of 3. You do a little stuff right, but it's mostly wrong, that's a 1 out of 3. Okay, and so that's what my grading will be, to give you some kind of insight to that. Now, staying with this, the second part of this question is, how far did it go? And that's where this one comes into play. And so how far does it go? I would do this. Distance equals to the average speed. And so maybe I'll come over here and calculate the average speed. I let it go, so that's a 0. And I just figured out that after 10 seconds, it's going 100 meters per second. And so it has an average speed of 50 meters per second. And so I'll come over here and say this is 50 meters per second for the average speed for 10 seconds. And so this is 500 meters. And so this thing would have dropped 500 meters. By the way, I would say that that's really tall. And for us to ignore air resistance for something like this, that's it's not even reasonable it would have reached a terminal speed by then. But that aside, I wanted to get a number that was really big, that you couldn't just do a couple of lines at a chart. And I would say, don't make 10 lines in a chart. Actually do the calculation here. By the way, this might be a good time to point out that equation, 1/2 AT squared, would be okay to use for this one. Remember I said this equation is usable only if the starting speed is 0. And that's what this problem is. And so if we put in a 1/2 and we put in the 10 meters per second, and then we put in the 10 seconds and we square it, 10 squared is 100 times 10 is 1,000, half of 1,000 is 500, and then the seconds cancel off and you get your meters. So not a surprise, it does work and we get the same answer. But I will say it again, I'm always a little leery of that equation, because that equation has the caveat of only being valid if the starting speed is 0. And a lot of our problems do have a starting speed of 0, but not all of them do. And so if you start using that equation without thinking about where it came from, you will find yourself, unfortunately, using it at an inappropriate time. In fact, maybe I'll illustrate that. As another example from this chapter, I might say something like this. How far did this falling object move between 8 seconds and the 10 seconds? Well, if that's the case, I would encourage this one again. I would say, all right, how far does it move? Well, the distance is equal to the average speed times time. Now I need to find the average speed. And so I need to take the speed that it starts and the speed that it ends. And in this case, my starting speed is after I have dropped it for 8 seconds, because I'm trying to ask here, how far does it move from the 8 to the 10? And I'm kind of hoping you can see it without me having to go through the math. If I redid this but put 8 seconds here, the speed would be 80. And so after falling for 8 seconds, it would be going 80. And of course, isn't that what we meant by acceleration being 10? Increase by 10 every second. So it starts at 0, and so 1 second later it's going 10, 2 seconds it's 20, 3 seconds it's 30, 4 seconds it's 40, 50, 60, 70, 80. And so I would say that in order to figure out the average speed, I'll take the 80. That's the speed at the 8 seconds, and then the final speed, which is 100, that's after the 10 seconds. That gives me an average speed of 90. So I have a speed of 90 meters per second on average, that's the average speed, during those last 2 seconds. So the time would be those last 2 seconds. And so 90 times 2 is 180. And so during those last 2 seconds, it would go 180 meters. That's what the math is telling me. And then also note that if you were careless and you use that equation, you wouldn't get anything close. And so I'll just cross it out. I won't even look at it. Because remember, it only works if the starting speed was 0. And that's what I wanted to point out here, that my starting speed is not 0, and so I wouldn't use that one. All right, well, I hope that's kind of helpful, kind of reviewing what we did in Chapter 2 and kind of helping you there with Chapter 2. How about Chapter 3? In Chapter 3, if you remember, Chapter 3 was Newton's 3 laws of motion. And so, let me just kind of recap the 2 easy ones. I call the first and the third one the easy ones. For example, if there's a, a test question that comes up and says, hey, I'm going to come up and push on this table. So I put my foot and I push. Which was greater, the push I did on the table or the table pushing back on me? And of course they're equal, right? That's Newton's third law. They're equal and opposite. Or this one here. Well, what if I had this fire extinguisher, if you remember this one from that unit? And just because I like to write it, I thought I would actually bring it out and write it again. Oh wow, this is really strapped up here well. Okay, didn't Ow. Oh. Can't even find the end of the crazy strap. Well, and I think it, yeah. There we go. All right. So, which would be a greater force? The force put on the carbon dioxide as it goes out the back? Or the force on me in this cart going that way? And this would be a good multiple choice question. The answer, they got to be the same, right? This is just Newton's third law. And my cameraman's just telling me here that the reason this was all strapped up is another instructor borrowed it. So now I'm worried that they used all the fuel. But let me give it a try here. I know when we did it, and 1, 2, 3. Oh yeah, there's still a lot of fuel. And so there it goes, tearing off again here. So like I said, I'd like to do it, so I thought I would put that one.